The light beam induced current LBIC method evaluates photovoltaic cells by measuring variations in wavelength, intensity, or light offset. It specifically observes the spectral dependency in complex cells such as triple junction gallium arsenide. There has been a modified approach created and named compressive LBIC, CLBIC. LBIC is accelerated by CLBIC, which takes use of the sparsity of solar panel imperfections and compressive sensing. Efficiency is increased by reconstructing current maps mechanically free of movement through the use of compressed sensing algorithms and pattern projection. Multispectral detection still requires a large number of observations. However, CLBIC dramatically accelerates detection according to numerous studies. An approach to further increase detection speed and lower sampling rates is multispectral CLBIC, MCLBIC. MCLBIC seeks to provide a quicker, more effective evaluation of photovoltaic cells by taking advantage of the correlation between multispectral maps and the spatial autoregression (SAR) model, and sophisticated optimization technique and the joint coding of a multispectral matrix are used in this method to quickly recover energy maps without additional hardware. The problem statement of this journal is the LBIC's method uses a long processing time which restricts its commercial applicability, particularly for multispectral data that necessitate repeated scans. The objective of this journal is to develop and propose a multispectral CLBIC and MCLBIC method that reduces measurement time and sample requirements compared to conventional CLBIC methods, and to provide a more efficient and time-effective assessment technique for photovoltaic cell characteristics. For discussion section, we will discuss about the MCLBIC method. The MCLBIC method is compared with the compressive light beam induced current CLBIC method, showing that the MCLBIC method has better recovery performance and requires a lower sampling rate for a given peak signal to noise ratio (PSNR). This graph provides a visual representation of the time cost associated with each procedure in the MCLBIC system across different sampling ratios. It demonstrates the efficiency gains achieved by the MCLBIC method and its accelerated detection speed compared to the CLBIC method. This graph presents the peak signal to noise ratio (PSNR) performance of the MCLBIC method under different spectral bands and sampling ratios, as well as the PSNR gain of the MCLBIC method compared to the CLBIC method. It provides a visual representation of the performance improvement and the potential for reduced sampling requirements offered by the MCLBIC method. In the MCLBIC method, these colors, red, green, and blue, represent the specific wavelengths of light used to illuminate the photovoltaic cells during the assessment process. Each color, red, green, and blue, corresponds to a specific spectral band, and the assessment of the photovoltaic cells under these different spectral bands allows for the detection and evaluation of various defects and characteristics within the cells. The MCLBIC method is effective in detecting major defects in photovoltaic cells with significantly reduced sampling requirements. However, the MCLBIC method has limitations related to the limited coverage of LCD spectrum, computational complexity, and the need for additional measurements to gather solar cell conversion coefficients for multispectral data. These limitations require further research to enhance the applicability and feasibility of the MCLBIC method in practical solar cell detection. Overall, the MCLBIC method shows potential for significantly reducing the time required for comprehensive detection and evaluation for photovoltaic cells contributing to advancements in the evaluation of photovoltaic cells in large-scale manufacturing process. In conclusion, through multispectral hybrid sampling, the proposed multispectral compressive light beam induced current (MCLBIC) approach greatly improves the speed at which photovoltaic cells may be measured. The MCLBIC approach increased sampling speeds and PSNR gain by selectively expressing multispectral flows and decoupling collected data. In order to decrease the number of observations needed and increase detection efficiency, the method takes advantage of the intrinsic sparsity of defects in multispectral measurements.